Hi, I am Dr. J. Glory, Associate Professor of Physics, Institute of Aeronautical Engineering. Today, I am talking about the BCS theory and applications of superconductors. So, in this session, we are going to discuss about the BCS theory and then applications of superconductors, and then we'll see the references. So, what is BCS theory? What is BCS stands for? So, Berling, Cooper and Schrieffer. So BCS theory. So these three scientists, that is Berling, Cooper and Schrieffer, proposed a microscopic theory that is known as BCS theory. Berling, Cooper and then Schrieffer. The three scientists proposed a microscopic theory called as BCS theory. So this BCS theory explains the superconducting state of a superconductor. That is how the normal conductor converts into superconductor and being in the superconducting state. How the conversion takes place from normal to superconducting state. So this theory involves the electron interaction through phonon as mediators. So this theory involves the electron interactions through phonon as mediators. So in normal conductor, that is the temperature of the normal conductor, which is T is greater than Tc, the normal conductor, the electrons will be moving in random way. So there is no any particular direction. The electrons can move any directions. So in normal conductor, the electrons will be moving at random directions. When they approach the vibrating atoms, the repulsive force predominates. So that they get repelled rather than attracted. So in normal conductor, the electrons will be moving at random. When they approach vibrating atom, the repulsive force predominates than the attractive force. So, as a result, they get scattered. The electrons get scattered from this vibrating atoms and resistance comes to existence. So, when they get scattered, then there is a term resistance acts. So this is the diagram which shows the scattering of electrons in normal conductor. So this is a normal conductor. So which is at usually T is greater than Tc. As we know that T is the temperature and Tc is the temperature that is critical temperature where the normal conductor converted into superconducting state. So this is a normal conductor and there is a atoms. So these are the atoms. So vibrating atoms. So when the electrons, these are the electrons, they are moving in random directions. When these electrons which are in the random directions approach to this vibrating atom, there is a repulsive force predominates than the attractive force. So that these electrons repelled by the vibrating atoms, so that they get scattered from the vibrating atoms. So when they get scattered from the vibrating atoms, so there it exists resistance. So when it is converted into superconductor, by decreasing its temperature. So normal conductor usually T is greater than Tc. So, normal conductor T is greater than Tc. When decreasing the temperature, when decreasing this temperature below Tc, so T is less than Tc, due to decrease in energy, that is when T is less than Tc, this normal conductor converted into superconductor. So due to decreasing, how it can be converted into superconductor? As at the temperature T is greater than Tc, it is being in the normal conducting state. As cooling, in the cooling, it below Tc, this normal conductor converted into superconductor. How the conversion takes place? So here, due to decrease in energy, the scattering of electrons by lattice vibrations also decreases. So the resistance will be decreases. So the resistance falls down to very low value at almost zero. So that when there is zero resistance, it shows infinite conductivity. So it converts into superconducting state. So when it is converted, that is when the normal conductor converted into superconductor by decreasing its temperature below the critical temperature Tc, due to decrease in energy, the scattering of electrons by lattice vibrations also decreases. So here in this diagram, the electrons are moving in random directions. When they approach the vibrating atom, these electrons get repelled by this vibrating atom because the repulsive force is predominates than the attractive force, so that these electrons are repelled by the vibrating atoms. So, if the temperature T is greater than Tc, the scattering of electrons be more, so that there is high resistivity. So there exists high resistance value. When it is decreased, when the temperature decreased to low value, due to decrease of temperature to the very low value, the energy of the electron also decreases, so that scattering of electrons also be decreased. So the scattering of electrons also be decreased, so that the resistivity becomes low. So to maintain stable state, the electrons get paired up and are known as Cooper pairs. The pairing of electrons can be well understood by considering the electron-phonon interactions. So this means that electrons traveling in a solid interact with lattice vibrations by virtue of electrostatic forces between them. The oscillator distortion of the lattice is quantized in terms of phonons. The oscillator distortion of the lattice is quantized in terms of phonons. These interactions is called electron-phonon interaction. So this interaction leads to scattering of electrons and hence causes a change in the electrical resistivity. So this electron-phonon interaction leads to scatter of electrons and it causes a change in the electrical resistivity. So it is assumed from the BCS theory that the electron-phonon interaction causes the Cooper pairs. So likewise the Cooper pairs are formed. So when electron with a wave vector, how these Cooper pairs are formed? So here BCS theory tells that they assumed the electron-phonon electron interaction causes the Cooper pairs. So how the Cooper pairs are formed? When electron with a wave vector k1 encounters a lattice ion, it suffers Coulomb interaction. It suffers Coulomb interaction. So suppose we are taking an electron having wave vector k1. So this is a electron. This electron with k1 wave vector, it encounters a lattice ion. Then this electron suffers some Coulomb interactions. It suffers Coulomb interaction. As a result of this Coulomb interaction, the momentum of the electron decreases by an amount proportional to K1 minus Q. So because of this Coulomb interaction, the electron's momentum decreases to K1 minus Q. And the lattice is set to motion, gaining a momentum from the electron proportional to Q. The lattice vibration is quantized and characterized by energy packets called phonons. Another electron with a wave vector K2 may enter in this volume and this electron interacted with the distorted lattice and gains momentum. The gain depending upon the phase of the vibration at that instant, so the electron energy is lowered. The lowering energy indicates that force between the electrons is attractive and the interaction is through phonons. Therefore, it can be thought that electron with wave vector k1 emits a virtual phonon q, which is absorbed by the second electron with the wave vector k2, and the two electrons are scattered with wave vectors k1 minus q and k2 plus q. So the process is a virtual process and the energy is not conserved. So this process is very rapid with emission and absorption of phonons. The short-lived phonon is called virtual phonon. So here the two electrons should have equal and opposite spins and their energies are the same. Then the interaction between them is attractive. As a result, such attractive interaction, there exists pairs of electrons called Cooper pairs. So that Cooper pairs can be denoted with K up and K down. Therefore, the electrons in a superconductor are in the form of Cooper pairs. So a Cooper pair, what is that Cooper pair? Cooper pair is a system of two electrons having equal and opposite momentum and spin K up and K down. The energy of the pair is lowered when compared to the free separate electrons. At low temperature, the Cooper pair's interaction with the positive ion core almost vanishes and hence the resistivity becomes zero. So thus the conductor becomes a superconductor. So you can see here the electron with the wave vector K1 emits a virtual phonon Q, which it is absorbed by the second electron with the wave vector K2. And the two electrons are scattered with wave vectors K1 minus Q, K2 plus Q. So these two electrons got paired up. These two electrons have same energy and they have opposite spin. So a Cooper pair is a system of two electrons having equal and opposite momenta and spin. So in this diagram can easily understood. So here is a electron having wave vector K1 when interact with the positive ion core, it suffers Coulomb interaction. So that the momentum of the electron decreases by a momentum which is proportional to Q1 minus Q. Q1 minus Q. Now, the lattice set into motion, gaining a momentum Q, from the electron which is proportional to Q, which is proportional to momentum, gaining a momentum. So, lattice is set into motion, gaining a momentum from the electron proportional to Q. So, the lattice vibrations is quantized and characterized by the energy packets called phonons. So, now another electron which have the wave vector K2 interact with this distorted lattice and gains momentum so becomes K2 plus Q. K2 plus Q. So these two electrons get paired up which have equal and opposite spin. So they causes superconductivity state. So these two two electrons got paired up and becomes as a Cooper pair. So because of this Cooper pair, the normal conductor conductivity will be increased because of decreasing its resistivity. So the resistivity will be decreased because when lowering the temperature, the scattering of electrons also decreases so that the resistivity decreases. So here the interaction between them is attractive. So the two electrons that is having wave vectors K1 minus Q and K2 plus Q, between these two are attractive. The interaction between these two electrons are attractive. So resulting that there exists a pair of electrons called Cooper pairs. So what happens when the normal conductor's temperature is reduced to very low, that is below Tc, critical temperature? The Cooper pair's interactions with the positive ion cores almost vanishes. The Cooper pair's interaction with the positive ion core almost vanishes so that the resistivity becomes 0. The resistivity becomes 0. So that the conductor becomes a superconductor. So T is greater than Tc. Here T is less than Tc. Here the scattering of electrons are more. Here scattering of electrons decreased. Here scattering of electrons are high, that is more. Scattering of electrons are more. So at very low temperature, what happens? The Cooper pairs are vanished. So because of this, resistivity is decreased. Resistivity is decreased. So at very low temperatures, the Cooper pairs interactions with the positive ion cores almost vanishes, so that resistivity becomes 0, so that normal conductor converted into superconductor at very low temperatures. So the Cooper pairs can, so this is the superconducting one. So the normal conductor, when cooled to very low temperature, then we can see the pair of electrons, which called as a Cooper pair. So this is the diagram which is related to the formation of superconducting pair electrons in superconductors. So here we have a positive ion cores. When the electrons approach to this positive ion core, it suffers Coulomb interactions. Because of that interactions, the electrons gains and loses some momentum. So that there it has been two types of electrons, K1 minus Q and K2 plus Q. So when this electron approach to positive ion core, it loses its momentum, so that it have K1 minus Q of momentum. Then another electron which approaches this vibration, that is lattice set of lattice, when it is approached to this, it gains some momentum, so that it becomes K2 plus Q. So these two electrons with having the vectors K1 minus Q and K2 plus Q got paired because they have equal and opposite spins, and there is a attractive force acting upon them, so that they get paired up and becomes as a Cooper pair. So when the temperature is decreasing to very low temperature, these two electrons, that is Cooper pair, these Cooper pairs almost vanishes, so that there is no resistance takes place. There is no resistance. So when there is no resistance, so the conductivity will be more. So infinite conductivity at low temperature we can observe, so that the normal conductor converted into superconductor like this. So because of this vanishing of Cooper pairs, no resistivity takes place. So it acts as a superconductor. So these are the paired electrons. These are the Cooper pairs. Cooper pairs. These are the Cooper pairs. So when electrons got approached to the positive ion core, then Cooper pairs are Then coming to the applications of superconductors, we can use the superconductors in many cases. That is, few of them we can see here. Electric generators. In this electric generator, superconducting generators are smaller in size, with less weight, consume very low energy. Electric generators, there is superconducting generators. They are very small in size, with less weight, and consume very low energy. So the low loss superconducting coil is rotated in a strong magnetic field. So this is the basis of a new generation of energy saving power system. Then magnetic levitation. Diamagnetic property of a superconductor is the basis of magnetic levitation. So this effect can be used for high speed transportation. So how the diamagnetic property can be exhibited by the superconductor? As HC, that is when the superconductor is placed in a magnetic field H expels the magnetic lines. It expels the magnetic lines because the magnetization is opposing the applied magnetic field, right? T is greater than Tc. Sorry, T is less than Tc. At very low temperatures, the superconductor, when placed in the magnetic field, the magnetization will be opposed the applied magnetic field, so that it acts as a diamagnetic material. So the diamagnetic property of a superconductor is the basis of magnetic levitations. So this effect can be used for high speed transportation. Then fast electrical switching. The application of magnetic field is greater than the critical magnetic field that changes the superconducting state to normal state, and removal of the field reverses the process. So this principle is used in the switching element cryotron. Then magnetic bearing. So mutual repulsion between two superconducting materials due to opposite magnetic fields is used in the construction of magnetic bearings without any frictions. Then superconducting susceptometer. A superconducting susceptometer consists of a superconducting material, that is a superconducting magnet, and then superconducting quantum interference devices. In short, we can call it as QUIDS. So the susceptometer, a superconducting susceptometer, consists of superconducting magnet and then superconducting quantum interference devices. So it is used to detect the variation of iron content in the human body. So it is used to detect the iron content in the human body. So many of the applications are there regarding to the superconductors, but few of the applications we have seen here. So these are the applications. The references or engineering physics by K. Tyagarajan, Tata McGraw Publications, New Delhi. Textbook of Engineering Physics, M.N. Avadhanulu, P.G. Kshesagar, S. Chandan Company Publications, New Delhi. Engineering Physics by Dr. M. R. Muga, Anuradha Publications, Chennai. Engineering Physics by P. K. Palanisamy, 4th edition, Scientific Publications, India Private Limited, Chennai. So these are the references which have been referred to this topic. In the next session, we shall go for another topic which is related to magnetic materials. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.